ago. Was that just been Friday? We talked about asteroids. Asteroids are rocky, and comets are rocky plus ice. So comets generally are going to be out here. Asteroids are kind of inner. Not to say that comets, like this slide says, that comets can't get nudged and kind of go into the inner part of our solar system. Where are the comets? The comets are two regions. We talked about the Kuiper Belt, where if this and this is the sun, and all the comets orbit the sun, kind of on a record, on a disk called the plane of the ecliptic. And the Kuiper Belt is also on the plane of the ecliptic. But the Oort cloud is even farther. It's more spherical. Those are comets. So you're going to see some even better pictures. I'll dim at least one satellite. These are pictures I took, because we need to talk a little more about comets. This is something I took recently, this past December, and it's just one of those where you take the camera and you open the shutter and kind of let it gather light. Well, these are stars, so the light from those stars in this telescope tracks. So it's tracking with the movement of the stars. The stars suddenly move. But this thing right here is the comet moving against the background stars. So you're probably talking maybe 2 minutes, of exposure, 120 seconds, maybe. So that's how far it moved against the background stars. And that's kind of zoomed in. Okay. So this happens. Comets get named. There are some comet hunters out there that are just like digital. They're like on automatic pilot. And I think it was one of those, so it's kind of nondescript. If a person finds it, their name goes with the comet. Isn't that cool? So I showed you mine because here in a minute you're going to see some prettier pictures of comets. My point about comets is comets won't fizz or anything unless they get close enough to the sun. I'm going to try to convince you of that. Okay? So comets, whether they're in the Kuiper Belt or the Oort cloud, have been there ever since our solar system's been an entity, about 4.6 billion years ago when the sun turned on. Comets they're usually out there, gravity keeps them out there, and they're usually out there unless they get jostled by a gas giant or a passing star. It's kind of weird. Okay. So comets kind of have, and we don't have time to do this semester for this class, but one exercise I've done with students recently is we can make a comet with basically dry ice. Dry ice is carbon dioxide, solid carbon dioxide that wants to fizz. Okay, carbon dioxide that wants to go ahead and so you do that and you put like chunks of rock in it and stuff, and you can hold it up next to a light source and it just kind of starts to fizz. So it won't fizz out there, it will fizz here, okay? So like this says, if you're like me, you look at the jet contrails, and you're like, oh, that's pretty cool, jet contrails and stuff. The reason they call them jet contrails is they're just kind of condensation particles as a jet moves up at upper elevations. But my point about a jet contrail is it kind of looks like a comet, but how long would you say jet contrails last? And to me, they kind of go across the sky in a matter of, maybe 2-3 minutes, the whole sky. Okay? And comets are like, just barely move night after night. I was going to say, so grab your phones, I'll grab mine too, or you can borrow mine, and pull up that program that you guys used on Thursday, and look in the search bar, and see if you can find anything about comets. Okay. Do you see any comets names coming up? Do you have it in the search bar? The top comet, how bright is it?
Was 11.9.
Plus 11.9. What's the name of that one?
The
Okay.
Waterman, or
Huh.
however you want.
Sounds foreign, yes. So 11.9 and such. You think that's very dim or very bright? Dim, very dim, plus 11. We'll be talking a little more about the brightness scale, but in real dark skies, if you have really good eyes, and the older you get, your eyes don't see, aren't as sensitive. In really dark skies, you're talking about a +6. That's kind of the limit. So plus 11. So if you click on those or whatever, just go ahead and play around with it. But if you click on them, you can go ahead and center it and see it in the nighttime sky and that sort of thing. While you're doing that, I was going to show you, there actually is a website out there. So many things I'd like to show you. There's a website out there called heavens-above.com. There's no www, I don't think. Heavens-above.com. And it does a lot of neat things. It will tell you when satellites are passing overhead, when the International Space Station's passing overhead. By default, it looks like this. Got so many different things on its webpage. But one of the things it will let you do is, there's a comment link. And it looks like this. So if you do heavensabove.com, and I'm not logged in, I could log in, but comments don't matter. But it will want to know your location, especially if you're trying to catch satellite in the International Space Station. Here we are, comets. It will tell you where the planets are. It's kind of fun. And I think it's going to give them in order of from the brightest to the dimmest. So maybe was this the one that you were looking at, the Stefan Otterman? Yeah. So brightest to dimmest, 46p, that was the one that we looked at. And then if you click on it, your sky map is more accurate than this, or I don't know about accurate, but it will show you, of course, what's this right here? What's the red? It's the Big Dipper. Yeah, can't hardly make out the rest of the hand. That's the Big Dipper. So this box right here is a general region, especially with binoculars. When the comet's relatively bright, 8.0 maybe. You can use binoculars to kind of see it, sweep that area. But one thing I was going to show you is if I go ahead, that's February 4th. Look how the box moves if I go to 10 days from now and update it. So the box moves with the different dates because the comet is just barely moving. So comets, my point is 10 days and you can see that it didn't move very much. So, all right. Okay. What else? So the anatomy of a comet, you have it only fizzes when it gets close enough to the sun. And it will create it'll create a tail, the comet tail, and it will create what's called a coma, kind of the circle around the little icy rocky thing. The icy rocky thing is called the nucleus. We have actually had spacecraft that had visited comets before and gathered space dust and brought the space dust back, and it's just amazing what we can do. So that's kind of how a comet does. This is actually a photograph of a comet. You're going to see some more photographs of comets, and they all have different personalities. The tails, actually, there's two types of tails. There's an ion tail and a dust tail. The ion tail is straight, the dust tail is curved. One of the things I'd like you to know about comets, and this figure is trying to show you, these are real photographs of a comet. Notice that the closer it gets to the sun, notice it fizzes more, right? When it's away from the sun, not so much. It has like a highly almost what they call a hyperbolic orbit where it comes close to the sun. There have been comets that went kamikaze. Comets like went into the sun. I think that's pretty fun. But check out the tail, okay? So here we go, April 26th, May 2nd. It's definitely going kind of from, I guess that'd be counterclockwise. They kind of have different trajectories. But notice that the tail is not like a kite tail. The tail is not going behind it, the direction it's moving. One of the things we just briefly talked about, we talked about the sun was solar wind. The solar wind is what's driving the tail to fly out. What direction is the solar wind? Well, in all directions. So regardless of the direction the comet's coming, that solar wind is going to blow the tail away from the sun. What else? So Comet Ison. I don't know if you can kind of make out the white tail, but then there's like a blue tail on the right side, kind of. Comet McNaught. Now the difference between Ison and McNaught to me is McNaught is all coma. Ison has a lot of tail. Comet Lovejoy. Okay, so pretty cool. So we have these three M things, and the thing we've talked about in here already was when we talked about asteroids, like asteroid belt between Mars and Jupiter. Asteroids are rocks. Okay, comets are rocks with ice. A meteoroid, you get the asteroid, meteoroid, got the oid thing ending. They're very similar. The only difference is size. Okay, so meteoroid is just an asteroid, but it's smaller. Okay, so meteoroid is a space rock. A meteor is a very short event. A meteor is a streak. It's a blip. So of these three M things I'm going to talk about, a meteoroid lasts a long time. It's a space rock. A meteor is actually when a meteoroid falls through Earth's atmosphere. It kind of blows. It's a streak. Meteor showers. We're talking about meteor showers in a minute. What is a meteor shower? And I had meteor showers in my dreams, and they're just here. Okay. So a meteorite is what this is. Meteorite and meteoroid last a long time. A meteorite is a rock from outer space that has enough of it has survived the Earth's atmosphere that you can pick it up. Well, I can pick that one up. You can get a lot. You can make a lot of money on meteorites. Okay. Then somebody's real clever. Sometimes meteorites are really meteor-wrongs. Get it? Meteor-wrong, meteorite. Yeah. So they look like it. And actually, I've got one in my office, and I thought to bring it, but no, because it's somebody on staff here said, this is not, or this is not Libby, but said, is this a space rock? Is this a meteorite? And you can go online, and actually there's a list of characteristics to see if the rock is actually extraterrestrial. Anyway, so we have had impacts in the past. Now, when I think of impact craters, I think of the moon, because the moon has a lot of impact craters on it. But this is an impact crater that happened, I don't have the date up here, it would have been millions of years ago, I want to say, in Arizona. And I think there's a central peak there, too. But the reason it's still there today is it's not on a place where it got resurfaced because of plate tectonics, and the weather didn't beat it down yet. Okay. So, meteor shower. So meteor is short-lived. Meteoroid, meteor, meteorite. Okay. But even, I'm going to talk about meteor showers here in a minute. So if a meteor is basically a meteoroid or an asteroid falling through the Earth's atmosphere and creating a streak, that's a meteor. That should happen in dark skies. You should see one about every 10 minutes, about one every 10 minutes. And that's not a shower, that's just normal. Our Earth actually picks up a lot of weight each day from crap falling through the Earth's atmosphere. Okay, it's getting heavier and heavier. I think that's kind of neat. Instead of finding meteorites, which might be meteor-wrongs, you might consider these like micrometeorites, where you can look it up on the internet, but they're like almost like little sand crystals that you should be able to find. So what happens during a shower? Well, this is what happens during a shower. So kind of get your bearings. We have the sun. okay? And we know that the Earth orbits the sun counterclockwise. So here's the Earth orbiting the sun. And this extra oval up here, that actually is the path that a comet has taken. So check this out. Meteor showers are related to comets, mostly comets. So what happened, we know that as the comet, this one's going this way, I can see kind of the lines. As the comet got close to the sun, okay, it started to fizz. It fizzes, we see it, okay. It actually leaves some of its guts behind and it goes about its way. Okay, it's gone. But it left some debris, some comet debris there, which is just perfect for the Earth to run into and for that debris to fall through the Earth's atmosphere and create those streaks. So meteor showers is when the Earth is passing through a debris field, and that debris field is most likely left by a comet. Sometimes it's an asteroid. So I just think that is so cool. And we know that as the Earth orbits the sun, we kind of have, we do the season thing. So a certain place is the summer solstice, a certain place is the winter solstice. We have spring and fall there. But my point is that it's a seasonal thing. So each year when we come to that same debris field, we're going to see a bunch of meteors. Okay? Meteors then actually kind of have what we call like a radiant. They have I don't know if you guys can see kind of the background stars and see kind of the things of light coming from kind of a similar location. That similar location then is what we go to name the meteor shower. So here we go. We jumped right down here. Orion. You guys recognize Orion? It's a constellation. So there is a meteor shower that appears to come through Orion. It's when the Earth, as it orbits the sun, it's around October. Specifically October 22nd. Thereabouts. When the Earth is in that position relative to the sun, we're going to have an Orion meteor shower. I was looking at this and thinking, okay, this spring, what do we got coming up? Not much. Okay, so yeah, if you kind of divide this into spring, summer, fall, and winter, we have very few in the spring. We have the Delta Aquarids in July, and then we have a bunch in the fall and some in the winter. So those are meteor showers. Now, if you, my best thing, I bet that app, does that app show you meteor showers too? My best suggestion, if you want to catch a meteor shower, is to kind of look it up. Did you guys? Yeah. What happens if you click on one? What information does it give you? I'm trying to see if it tells you like how many you should be able to see. Oh yeah, rate per hour. Yeah, peak hour and rate per hour. You should look at that rate per hour, because if that rate per hour is like really low, like it's not worth it. Click through there and see if the meteor shower, see if you can come up with the Perseids. Is the Perseids listed on there? Scroll down. Let's see it yet. Oh, it's alphabetical. I see Perseids. Okay, so how many per hour?
100.
Yes, that's my point. Yeah, so that kind of tells you whether it's worth getting up. Now, meteor showers, if you read about them, they will say you should start watching. I get too tired, so I get impatient. I watch from about 11 p.m. to maybe 2 a.m. Don't use a telescope. Don't use binoculars. Just use your peripheral vision. Okay? So it's a thought. The darker the skies, the better. So that's pretty cool. Okay, guys, on to part 4. Dun, dun, dun. I feel like we've kind of been talking a little bit already about constellations. We'll talk some more. So everybody got this PowerPoint slide?
I forgot mine at home.
Did you?
I think I had it on.
I might have an extra one. This is a real short one anyway. I don't have an extra one to give you.
It's all right.
Okay. So before we talk more about stars, I want to talk about something called parallax. And parallax, when I hopefully describe it to you, you'll be like, oh, that's why we get these wonderful patterns of stars, and the stars don't get all kabobbled as we orbit the sun, as the Earth orbits the sun. So in order to talk about parallax, I think this is my next thing. Okay, so here you got, everybody gets to do this. Okay, what you do is you hold your finger, let's see how to do this, yeah. Hold your arm out. Now I'm looking this way, but you guys look this way. Hold your arm out. Need a picture of this. And go ahead and kind of look at your finger where it is against, this is going to be your background. So for you, this is the background, for me, it's the background. Okay, and then go ahead and close one eye and close the other eye. And for me, my finger kind of moves this much, kind of against the background. You guys, and eye doctors would tell you have a dominant eye and a recessive eye, and the one where it moves the least is actually the dominant eye. So me, it's my right eye. Does it move a little bit for you? Okay, take that same finger, same kind of background, and now move the finger close to you. Don't go cross-eyed on me, okay? And then do the same thing. Left and right, left and right. And for me, as I kind of go back and forth, left and right, instead of like moving this much, it moved like this much when it was closer. When it was closer, my different eyes moved this much. When it was far away, it moved this much. That is parallax. So in other words, when you have it far away, you're kind of changing your eyes and it doesn't move much. But when you move it close to you, you change your eyes and it does move a lot. Now, changing your eyes is actually kind of like what we say, changing your relative position. So that's parallax. So not the whole eye thing, but we have two people looking at a tree. This is the thing of interest. And this guy says, oh, I see the tree over here against this peak. And the girl says, no, I see the tree over here, kind of to the, I guess it'd be to the left of the peak. She sees it to the left of the peak. He sees it to the right of the peak. And actually, I think those might be even different peaks. But they see that nearby tree, this is the nearby tree, they see it at two different locations. Now, if we take that tree, and if we move that tree back by the mountains, check this out. If the guy's standing here, or the girl's standing here, and the other person's standing here, if that tree is way far away, kind of like if you put your finger way far away, it doesn't matter when you change your position, the observer's position. It's like way far away. You get that tree kind of close, and oh yeah, it really does make a difference. Like what we're looking at is something of interest against the background. Okay. So I actually brought this. Let's see if this will work for us. So this is going to be my star. And there, yeah, you guys don't have to look here in a minute. I just want an excuse to use my pointer inside. Okay, so this is my star. And the two places I'm going to stand will be, well, I'll just kind of guess over there and over here. Okay, so right now that's a relatively nearby star. Check this out. Okay, so I'm going to go over here and I'm going to hopefully not get any of you guys. It won't hurt really. I mean, it's just, yeah, but your eyes and stuff. Okay, so I'm pointing at my star and my star is like, so look where it is with the background stars. Okay, there it is. Okay, that's my background stars. Okay, now I'm going to go over here. I'm touching the star, and here it is. See where it is? Okay, so that would be like the guy and the girl, two different locations, looking at something kind of nearby. Now, I'm going to go ahead and take my star. Say my star is farther away, and I'm going to go back and forth and see where it is against the background stars. So when I did that before, I was kind of here-ish. So you're looking at right about there. And you're looking at right about here. So to me, again, I move it far away, and this is kind of the distances it moves when I'm at different locations here. Versus if it's pretty close, I went from here to over here. Okay. So that's parallax. You see, I guess put another way, we see more parallax when it's closer. And the parallax goes away when the object's farther, even part of the distance background. So here we go. We can have a similar thing with the Earth. What's this have to do with stars? Well, and this might kind of go against one of the things that you already think about stars. You know, if you're like me, like, oh, I see the Big Dipper. Oh, that's awesome. Or I see Orion, I can recognize that pattern of stars. It's a set pattern of stars. Well, there are some stars, if they're close enough, they're going to move against the background stars that are way far away. So here's such a star, okay? So I put the word up there, words to move. So here's the deal. We know that the Earth is actually changing its position in space as it orbits the sun. It's just the deal of it. Kind of like the guy and the girl, different locations. Well, if the star is relatively close, like they're trying to show this white star here is, in January, we would see that white star here against these, what are they, 7 background stars. Then when the Earth is over here, the star is going to move. Okay, it's actually going to look at a different position against the background stars. That's parallax. And we actually do see that movement in some stars because they're relatively close. It's not because the star's moving back and forth. It's because we're seeing parallax. All right, so with sky maps, like you guys have the Sky Safari downloaded on your phones, a lot of times you can choose which set of constellations it will go with. By default, we go with the Western set of groups of stars, and it ends up that we end up with 88 different constellations. Now that would be, we don't see all the constellations because we're limited by, actually, as it turns out, we're limited by our latitude. So many of the constellations are associated with Greek and Roman mythology. So we already know, I was thinking about this today, why don't we see, what stars will we see? Well, it depends. It depends on the time of day or time of night that you're looking at the sky to see stars. It depends upon where you are as you're orbiting the sun, because here we're going to see these stars at night. Over here, if this is the sun, we're going to see these stars at night. And it also depends on your latitude, where you are relative to the equator. So this thing that I brought in a few times, I kind of alluded to it the other day when we had our sky maps. This is called the celestial sphere. So it's not a real deal because the problem with this is it kind of makes it look like all the stars are equidistant from the Earth. That's not it. But it kind of feels like they are, okay, because we don't see parallax in most stars because most stars are far enough away. Kind of pass this around. I think the different colors mean, I think their sizes. I don't know how to look at it that much. You kind of see this kind of yellow part, that yellow part that goes all the way around, that's actually the plane of our galaxy. That's what we call the Milky Way. We call it the Milky Way. Of course, we're in the Milky Way galaxy. That's looking into the disk of our galaxy. So that's called the celestial sphere. It's a model. It's not, like I said, the real deal. Actually, this kind of could freak you out because now it's back to what looks like a geocentric model, where the Earth is in the center and the sun orbits the Earth. That's not the real deal. We know that. But that's kind of what it looks like. So celestial sphere is a scientific method or model. So the Earth is placed in the middle of the celestial sphere. Movement of stars as the Earth rotates on its axis can be, using this model, seen as we rotate the celestial sphere around us. What is rotating? And this actually is consistent with one of the things we know throughout the course of the night. We said the Earth's axis of rotation is tilted, and the other day I had a little sticky note up here. It's pointed towards a star called Polaris. That's our North Star now. It won't always be our North Star. But throughout the course of the night, as the Earth spins, it's going to look like the stars are going counterclockwise around Polaris. And that works with this model. What's this word right here? It starts with letter E. What do you think? The plane of the, I said a little bit ago. Ecliptic. Yep, the plane of the ecliptic. Yeah. So it's also, the plane of the ecliptic is tilted 23.5 degrees outside of what we call the celestial sphere equator. So I don't know if you can kind of tell the Earth's equator in there is kind of, Earth's equator in there would be perpendicular at a right angle to its axis of rotation. So here we have the Earth's equator, and it extended out here, and there's the celestial sphere equator. Here we have the North Pole, and that's the celestial North Pole. Here we have Earth's South Pole, that's the celestial South Pole. Okay. And I'm not necessarily going to test you over it this semester, but what we can do is take this celestial sphere, which has those awesome 88 constellations on it, and we can slice and dice it so that when astronomers are trying to say where something is in the sky, we can refer to it on the celestial sphere. That sky map that you guys have been using, that Sky Safari, if you click on something, it will tell you the coordinates in right ascension and declination. It will tell you those coordinates, and those coordinates are a way to help you find it on the celestial sphere. My go-to telescope, once I have it calibrated, and if I know where a comet is, if I know the coordinates of a comet, which would be its right ascension and declination, I just tap it in there and it goes, comet. It's cheating, but it's okay. I'm not beyond cheating. So I just kind of finish up with some constellations. Let's see. Bowl is the word there, and bowl and pointer. So there are two dippers. The Big Dipper is a lot more pronounced. The Little Dipper is hard to see. I know it looks like, let's see if you guys can see this Little Dipper right here. It looks like there's similar brightnesses, but I have a hard time. In fact, a way to kind of test how clear your skies are is if you can see all 7 stars in the Little Dipper, you're like, sweet. If some of them are kind of coming out and going and coming, you kind of have probably some clouds in the way. Doesn't mean you can't enjoy the night. But the Big Dipper is a good way to find a few things. The Big Dipper, like I said, is kind of usually pronounced. Sometimes the Big Dipper will be kind of low here on the horizon, and sometimes it'll be kind of up high on the horizon. Because if I'm pointing, this is Polaris, this is the North Star, the Big Dipper is actually going to go counterclockwise around Polaris. So Polaris you can find from the Big Dipper. Like this says, we're going to use the bowl part of the Big Dipper, and we're going to use the 2 furthest stars, and then the next star that you can see with your naked eye, basically, that's going to be Polaris. So that'll help you find Polaris. And then Polaris is the last star in the handle of the Little Dipper. So one of the misconceptions is that Polaris is like, oh man, it's got to be bright because it's our North Star. Well, no. And like we know, Polaris won't always be our North Star, and no, it's not that bright. It's important though. So what's this word right here? Throughout the evening, stars appear to rotate about what star? Polaris? Yeah, counterclockwise. Okay. So I grabbed another figure. I think this one might be from this textbook. I get figures from different textbooks. The yellow here actually is trying to kind of show you the outline of the constellation. The red is showing you the boundaries for that constellation. How many constellations are there? 80? There's 80 constellations. So these are, and they're irregularly shaped, and they're not even at all. Right now, actually, I haven't been out for a while, but we have a summer triangle, winter triangle, probably the winter triangle now, and it's from 3 stars and 3 different constellations. Right here, Sirius is actually the brightest star in our nighttime sky, brightest star to us. And it is part of the constellation Big Dog, Canis Major, and he is the dog to Orion. So that's one of the 3 stars. We have Betelgeuse in Orion, and then we have Procyon in the little dog, Canis Minor. Oops, or this triangle. And before we know it, it will be summer. So we have a summer triangle too. And this yellow part right here, okay, this yellow, I said, what did I say this was?
The asteroid belt or something?
Nope, not the asteroid belt. It's the plane of our galaxy, so it's the, which galaxy do we have? Milky Way, yeah. So we generally call this the Milky Way. And on that sheet that I gave you the other day, it's got kind of a gray area. That gray area on that sky map sheet, this is what I'm trying to say. This gray area is the Milky Way. So you would expect to see, and I mention that because actually here are some constellations that are in the Milky Way. And if you ever get a chance, you're outside and you see the Milky Way and you have a pair of binoculars, I know that's a lot of ifs. It could happen. Take your binoculars and look at the Milky Way. You see all sorts of little tiny stars. It's just beautiful. But anyway, summer triangle, again, made up of 3 stars from 3 different constellations. We have Deneb in Cygnus the Swan, and the swan's looking like it's flying up the Milky Way. Then we have Vega in the constellation Lyra and Altair in the constellation Aquila. So, all right. So we got 2 in assignment. We are going to go ahead and take a look at part 5. So this question will be due when we meet again on Wednesday. Yeah, your lab is on Thursday, right? Yeah, actually you're taking tests this time. You guys have any questions about the test yet? I know you probably hopefully kind of thinking what you want to do to prepare.
We can make it, it's like a sheet of paper, right?
Yeah, just a whole
It's
sheet
like
of
that
paper.
from my other one too.
What's that?
It's like that from my other one too.
Well, actually, your evening hybrid this
Yeah.
semester, what I said, you can bring like a whole notebook of
Oh,
handwritten
okay.
stuff.
I started on that yesterday, so I was just making sure.
Yeah, for that one, a whole notebook, and for this one, a sheet.
Okay.
And you still own 4x6 sheets.
So everything on the study guide is probably what's gonna be on the test.
Yes, yeah, the study guide, and we haven't gotten all the reviews that, all those terms, so we'll kind of see what we get for Wednesday. But yeah, so I would take those from the study guide and kind of find them in my PowerPoint slides.
So if they're gonna store them in the book or not, sort of like what?
If there is a book, they're also my slides, so you can't go wrong finding them in the book. But the question will probably be more oriented to how my slides were. Does that make sense?
So the homework questions won't be on there?
Not necessarily, no. You kind of hit and miss. Questions may or may not be. Okay. So let's take a look at stars. I couldn't resist the other day. We were we shop at our Goodwill a lot. I don't know, they have such cool things. And so actually my daughter was looking for a present for my mom, her grandma, at the Goodwill, and she found there was a pair of pictures or little canvas things that said, "Twinkle, twinkle, little star, don't you know how loved you are," or something like that. So I got one and my mom got one. So something about stars that just make me smile. So one of the things we need is we're kind of leaving our solar system a little bit more, is we need to talk distance. We talked that there is something called an AU, astronomical distance. That's the average distance between the Earth and the Sun. But we need to take it up a notch, and this says Buzz Lightyear, okay? The word is distances. In order to describe how far away a star is, we need to talk about something called a light year. So this is this little image up here is trying to kind of show you, when you turn on a light, you think that, like if you're standing over here waiting to get the light to get to you, you think that simultaneously, and it feels like it, when someone turns on a light, you see it. Duh, right? But here's the deal. If the light's powerful enough, now that's part of the catch. If the light's powerful enough, there's going to be a delay because it takes light a certain amount of time to get from point A to point B. If the light's powerful enough. In fact, traveling at the speed of light, okay, for instance, here, this might help. Okay, here we go. Earth and Moon. If you are on the moon and you have a powerful enough light, you shine it back to the Earth, it's going to take 1.29 seconds for the light to get to you. Okay, 1.29 seconds. So we say that the distance between the Earth and the Moon is 1.29 light seconds. Here we go. A little bit farther, 8 minutes. Okay, so if you're on the Earth shining something on the sun, it's going to take 8 minutes to get from the Earth to the sun. Okay, so it's 8 light minutes. Earth to Mars, 13 light minutes. So kind of stepping out, instead of light seconds or light minutes, light years would be the years it would take for light to get from point A to point B. The closest star we have is Proxima Centauri, so it's in the constellation Centauri, and it takes light 4.3 years to get from that star to us. So a lot of times students be like, hey, so you mean if it's gone away, like some stars do blow up, I don't think this one's going to, but if it's changed, then there's going to be a delay of about 4 years before I see the change, and that's right. So we kind of have this like kind of look back thing. We're looking at it as it was 4 years ago. So here's one for you. So just now there are other galaxies. I think we kind of talked a little, I don't know if we did yet or not, but we said that our sun is a star, a member of the Milky Way galaxy. And the structure of a galaxy is a lot bigger than the structure of our solar system, right? So if you are one side of the galaxy, let's see, Earth to the other side of the galaxy, yeah. So this is an edge, it's about 100,000 light years side to side. But if you're trying to go from where we are to the edge, about 52,000 light years. But the galaxy itself, the diameter is about 100,000, light years. That's a lot. I don't know about you, but I'm not planning on living 100,000 years. So that's an important concept, a light year. So a light year is a distance. All right, we're going to do, just going to keep going here. We'll be talking more about this on Wednesday, but the idea of a star being born is similar to what we already kind of talked about, our solar system. Remember we talked about the condensation theory of our solar system? Condensation means like water going from a vapor to a liquid. So in this case, I kind of talked about the snowballing thing, the snowballing phenomenon where we have basically a solar nebula, and it's down here. We had a solar nebula, stuff kind of came together, kind of got tracks, the tracks made the planets, the center thing made the star. Okay. So here's the deal. If you take this this is actually kind of just our solar system. If you take that little cloud, and if you make it like, I have a cloud here, it's going to be a star. I have a cloud here, it's going to be a star. I have a cloud here, it's going to be a star. That whole thing actually is called a giant molecular cloud. So we can have something much bigger than solar nebula, and it's going to birth a lot of stars. Okay? So if that's the case, then you can get like families of stars that were born about the same time. So this kind of from left to right, you might have heard before the Pleiades, this blue one right here, it's got kind of a blue cast to it. You can kind of see the gas clouds here. They wouldn't look like this through binoculars, but so this is the Pleiades, the Seven Sisters, Messier object number 45. This is an open cluster, and this is a globular cluster. But these are stars that were actually born with the same phenomenon, but we had all sorts of different like little little nebulas within a giant molecular cloud that could birth a lot of different stars. So they're a family. A family. Along those lines, up here, the word is companion. Up there, and we're going to talk